Okay.
Welcome back, everybody. That's our second in the semester series, ICAR CCPO, Resilience and Physical Oceanography. So we get a little bit of both worlds slightly today. Tom Allen, one of your co-organizers, and I'm happy to present Dr. Sina Razzaghi Asl, uh, new assistant professor of hazards and environmental geography here at Old Dominion. Sina comes with a very accomplished record. Uh, and he's most recently come from Princeton University, where he was a postdoc scholar. He's got a PhD from Temple University and from University of Tehran, kind of combining landscape architecture in the past. He's got some personal interest in that direction, and also, you know, environmental hazards and geography and GIS. So we're looking forward to a lot of contributions from him on the research front at ODU, in sync with ICAR and environmental geography, but also in terms of AI and data science. So think you'll see quite a blend of these in his talk today. With that, we'll have questions at the end. So I'll hand it off to you, Sina, to take it away.
Good afternoon. Thank you so much, Dr. Allen, for having me, and it's great to be here. Today, I'm gonna share some of my research that I have been working on over the past 2 years or so, examining social vulnerability and nature-based solutions to flood risk, and with the special focus on equity, scale, and socio-ecological, perspectives. So briefly, I'm an assistant professor of geography and also affiliated faculty with the Institute of Coastal Adaptation and Resilience, or ICAR, and previously was a postdoctoral research associate at the Center for Policy Research on Energy and the Environment, working with Dr. Eric Tate at Princeton University, and got my PhD in geography with the topic of impact of nature-based solutions on flood loss and vulnerability in Philadelphia metropolitan area, which was the case study for the research. And my research sits actually at the intersection of flood vulnerability, spatial analysis, and nature-based solutions with a consistent, emphasis on equity and decision making. So let's talk a little bit about some of the current challenges in these areas, uh, especially in flood research. We still heavily rely on, oversimplified social indicators, meaning that uh, a wide variety of research use discrete social indicators like race, housing tenure, income, age, disability, or something like that, or composite indices that average social conditions. Well, while in reality we know that flood risk is shaped by a kind of intersecting or overlapping different social attributes like uh, race and housing tenure. We have, for example, poor renters. We may have, for example, uh, black renters or something like that. So this is a reality that often we miss in our analysis. Another point is about the scale blind vulnerability modeling, which we see a widespread pattern in our vulnerability modeling approaches, and which is driven by data aggregation. And we know we always, for example, may face some modifiable aerial unit problems or ecological fallacy issues, which is an error of making inferences based on the for, individuals and household level based on some area, uh, based averages of social conditions at some coarser levels like census tracts or counties or, other course, resolutions. And finally, the topic that I'm going to focus on during this talk is about nature-based solutions optimization, which is another emerging topic, especially spatial optimization. How can we optimize different types of nature-based solutions like wetlands, mangroves, living shorelines, or something like that in our cities, in our coastal areas, in our, suburban areas to actually balance between hydrological performance, economic efficiency, or cost, and land use, challenges and limitations. So all of these challenges, raise a core question that I'm asking, which is about how can theory, inform geospatial and quantitative modeling better capture intersectional social vulnerability and support optimization of nature-based flood risk reduction. Uh, for today's talk, I'll structure my talk around three different research strands or questions. The first one is uh, about how intersectional vulnerability reshapes flood exposure modeling and what actually differences uh, might happen between discrete social vulnerability indicators, influences, and intersectional ones. And the second question that I'm gonna share with you is about how a scale actually alters relationships between vulnerability and disaster assistance programs. That here, I'm gonna focus on one of the uh, widely used FEMA's aid allocation programs named the FEMA Individual Assistance Program, that they allocate funding for repairing, for replacement, for renting after, huge disaster in the US. And finally, uh, this is a study about uh, nature-based solutions optimization to, to balance between what? Water retention capacity or runoff and actually cost benefit analysis in Gdansk in Poland. All right. Uh, the first study that was actually published most recently in Applied Geography is about intersectional flood vulnerability modeling, which we use a quantitative, modeling approach using the spatial machine learning model. And our premises is that actually uh, intersectionality has a relative long story in social theory, originating with uh, Black uh, feminist and critical race theorist uh, Kimberly Crenshaw's landmark in 1989, and has actually recently entered into the quantitative hazard research. And the key idea is that people actually experience flood impacts not as isolated, attributes like income, age, or disability, or housing tenure, but through intersectional social, identities. And the conventional or traditional modeling approaches, for example, and indicators like the discrete indicators actually obscure this interdependence. And to do so, we asked two main questions. The first one is whether intersectional social vulnerability could influence flood exposure differently than discrete indicators. And second, how this relationship between social vulnerability and flood exposure actually, you know, vary across different populations and indicator values rather than remaining linear and uniform, which we see, for example, in majority of previous research and results. We focus on California state because of its physical and demographic composition and diversity, which was a great and ideal, case study for this research. And also, uh, it uh, experienced widespread inland flood hazards, specifically due to climate change, land use and development, strategies, having an aging infrastructure, and some environmental governance, issues. And in the middle map, you see, for example, a map from California showing different buildings exposed to a 500-year flood return period, which is equal to zero point 0.2 annual chance of flooding in FEMA's terminology that I'm sure that most of you are familiar with this kind of terminology. And so it shows, for example, more than 1.5 million different buildings exposed to 500-year, flood return period. And California has 10 different administrative regions, which we took into account to see whether, for example, these relationships also differ between urban and non-urban areas. This is a general workflow for this study. And to answer our two questions, we first, combine American Community Survey demographic data, census tract level, with flood exposure data obtained from FATM 2.0, which is a raster dataset at with 10-meter spatial resolution showing flood depths, and also Microsoft building footprint data that we used. And finally, to account for density and differences between urban and non-urban areas, we actually adjusted this metrics with building density, and then use some different tests for spatial autocorrelation using Moran's eye and some collinearity, checking between different indicators, and used a kind of geographically weighted variance inflation factor, or VIF, to show, for example, whether this multicollinearity exists between different geographies as well, which is a kind of localized VIF. And finally, we use geographically weighted random forest, which is a machine learning model accounting for the spatial data and spatial weights between different geographies, and which differs from traditional random forest, which doesn't, account for spatial variations and local dependencies. And here you can see a spatial distribution or correlate place maps of different, indicators that we included in this study, including poverty, the percentage of poverty, renter, non-white, and in terms of intersectional, we use the percentage of renter in poverty, percentage of non-white in poverty, and non-white renter, which um, uh, contains our intersectional variables. And even visually, you can see, for example, how uh, different, uh, you know, these two set of indicators show the vulnerability in different areas. For example, I've added a black box showing, for example, for comparison between, for example, these different areas. And here, I'm going to show you some of the results. The left panel shows a global RF model. This actually table shows the relative indicator influence or the different rankings of our variables in terms of their importance that we calculate by using an increase in, actually mean squared error, which shows, for example, the uh, contribution of each indicator, the predictive outcomes of the model. And in the left panel, as you can see, the non-white actually ranks first, following by non-white renters and renters. When we move to local GWRF or geographically weighted random forest model, poverty rises up. And, non-white in poverty and non-white renters actually consistently remain the most top among, for example, almost some of the local, areas. And this kind of comparison shows, for example, the difference between two modeling approaches, which we see, for example, this difference. And it's also supported by the higher local explanatory power of local GWRF model, which is higher than the global traditional model. And also the lower error or lower, RMSE and lower MAE and lower Moran's I, which is for spatial autocorrelation. And this table shows these dynamics among different, 10 different administrative regions in California. As you can see here, we see a higher local R squared in mostly dense urban areas like San Francisco, Inland Empire, and Los Angeles County, compared to other, areas with lower, density. And here also we use partial dependence plots or PDP, which shows whether, for example, if one variable actually influence the predicted outcome of the uh, machine learning model by visualizing the marginal effects. And here you can see that we see some thresholds and nonlinearity between actually different social vulnerability indicators and flood exposure, which is a great point and one of the most important results of this study that shows actually vulnerability does not increase exposure smoothly, and it often shifts abruptly when, once, certain social conditions is reached. This is the main point, extractable from PDPs, which are great explainable, AI tools, and something like sharp, values that shows different threshold base and nonlinearity relationships. And in terms of takeaways from this study, we can say that intersectional variables have distinct predictive values versus, discrete variables. And in reality, actually, we may pay more attention to intersectional variables because social vulnerability is intersectional. Uh, and relationship between these indicators and flood exposure, um, as we found, are spatially variable and nonlinear and threshold based, depending on the some social, critical points or tipping points or cutoff. We see, for example, different pattern after and before this, points. And also we saw strongest, relationship in urban areas rather than non-urban areas. And finally, we can use geographically weighted random forest or geographically weighted, gradient boosting models or other ensembling machine learning models for accounting these dynamics because they can actually estimate local regressions. And also by using partial dependency plots, we can uh, actually map nonlinearity and non-spatiality between different variables, which if we use, for example, some conventional methods like geographically weighted regression or GWR or random forest or even spatial autoregressive models like spatial lag model, spatial error model, we may miss, for example, some of the most important, dynamics. All right. The first research that published in the annals of the, American Association of Geographies is about scale, influence in vulnerability and assistant, relationships and modeling. Here, for example, a core premise here is that scale fundamentally actually shapes what we see and what we miss when modeling vulnerability and disaster resistance. And here, household level data can best, capture true vulnerability because vulnerability is experienced and produced at household level data, not aggregated levels like census tract. So this is really, useful and important and critical in a vulnerability modeling or exposure modeling approaches. And also ecological fallacy, as I mentioned earlier, is a kind of error that we face when we make inferences based for individual and household level based on, our relationships observed in aggregated levels like census tract or counties. And the majority of research actually um, does not, handle, don't handle this kind of scale problems in their modeling processes. And here, scale dependency of social vulnerability indicators is another important fact because we know that some uh, actually variables might be scale sensitive, while, for example, some other might be robust across different scales. And this is something that we wanted to um, measure in this study. And we asked two questions. The first one is which social vulnerability characteristics best explain the receipt of disaster assistance. Here, disaster assistance, we mean the FEMA's individual assistant or IA program at the household level. And second, how do the spatial scale of analysis and aggregation actually influence this kind of relationship? Uh, we chose Harris County in Texas because it was severely impacted by Hurricane Harvey. Our focus was on Hurricane Harvey and in Harris County, and which was, highly flooded. And also, it is one of the socially diverse communities and, regions in Texas. And also, we have seen a large volume of FEMA individual assistance claims here after Hurricane Harvey, which we could use for our, analysis. This is the approach that we took for this, analysis. We compared the relationship between different social vulnerability indicators and disaster assistant, uh, you know, funding in three different scale and aggregation levels. First one was in household level, which was a native, actually a native, we can say native uh, fine scale resolution dataset obtained from FEMA. And then the to see, for example, the impact of aggregation, we aggregated this local IA or individual assistant data at census tract level, which we call the tract household. And third, we used ACS or American Community Survey, demographic data at tract level, which is a kind of aggregated, publicly available data set. And for controlling, we actually included two different measures. The first one, which we introduced, was damage burden, which was calculated by a division between property damage that we, got from the verified flood loss data from FEMA, and then value of property improvements from the same dataset. And flood depths, which was a Hurricane Harvey raster flood depths, which was produced by FEMA after Hurricane Harvey. And we use different spatial regression or spatial auto-regressive modeling approaches by doing some tests like Lagrange, multiplier tests to see, for example, which methods is uh, appropriate for this kind of analysis, including a spatial error model, a spatial lag model, and to see the impact of ecological fallacy. And finally, uh, we used a kind of variance analysis to see the coefficient stability between different models. This map shows bivariate maps the relationship between damage burden and flood depths or water level in Harris County. As you can see, for example, because of the data privacy and security, we were not able to show, for example, the layouts from the household data on the left side. And you can see, for example, the black rectangles indicating those areas with both high damage burden and flood depths. And if you can compare with two different, scale and aggregate the levels, you see so much difference and different patterns in these areas, you know, emphasizing the impact of ecological fallacy and scale. Here, actually, uh, uh, what emerged was striking because some indicators, reverse direction between different scale and aggregation, and some of them lose actually significance. For example, in terms of reversing direction, we saw household income was negatively significant at household level, while we saw, for example, in tract level was not significant. And for example, another one was household size that we saw significant at household level, while, for example, in other aggregated and coastal, resolution or scales, we saw not significant. And for renters, for example, the same pattern. So we found that disability, flood depths, and damage burden remained positively significant, and they were robust across different scales and aggregation, as we expected. Not disability, but for flood depths and damage burden, uh, there was no surprise. But for disability, yeah, we were surprised. We were shocked to see, for example, why disability, for example, remained positively significant, which shows uh, consistent pattern between different scales. And also we saw notable change in direction occurred with household income, as I told, and we uh, concluded that household level data reveal hidden vulnerability patterns. And here we see a variance analysis result that uh, shows whether, for example, different relationships or coefficients actually differ across different models. And as you can see, uh, disability, water level, and damage burden, are consistently positively significant across different models, regardless of the scale, while some other factors like renters and household size have a strong positive effect at household scale that weakens at coarser scales, which shows a kind of different pattern, which is really important in policy and research because we always, we, or practitioners or policymakers always, for example, do make decisions based on disaggregated levels, which sometimes may not show the actual real, compounding vulnerabilities. There are some takeaways both for research and, um, practice. The first one is the analytical scale is not just a technical detail, but it is a theoretical choice. Depending on our modeling approaches, depending on our context, depending on our objectives or goals, we should choose different, the scales. This is not true that we say that define level, household level data for, vulnerability is always good. It depends on the situation, depends on the scale that you are gonna, uh, propose some policies. And but we found that, and we believe that data aggregation can reverse or inflate these relationships, creating risk of ecological fallacy. And also, we understood that some vulnerability indicators are robust across scales, while others are scale sensitives, which actually requires scale alignment between, you know, our policies, modeling approaches, and objectives. And finally, I'm going to focus on nature-based solutions for flood risk optimization. Here, our premise is that nature-based solutions are defined as actions that work with natural systems like wetlands, and they can support, sustainability and resilience. But and they can, as studies show, they can reduce runoff, they can manage stormwater, and they have some co-benefits like biodiversity loss reduction, like, air pollution mitigation and something like that. But they might have some trade-offs for these services. And as we see, a lot of, optimization models and algorithms don't actually account for land use compatibility, cost efficiency, and water retention improvement at the same time. So this is a study that we did it in Gdańsk in Poland, and we asked two questions. The first one is that to what extent can the optimization of NBS enhance the water retention capacity? And actually, what kind of different NBS could be more impactful for both water retention improvement and lower, cost of implementation. This was the goal. And second, what trade-off actually exists between water retention capacity and implementation cost? We focus on Gdańsk as one of the coastal cities in Poland, shaped by water and flood exposure. It's very similar to Norfolk, actually. And so the in terms of the urban layout or landscape or diversity, and high exposure to pluvial flooding from intense rainfall, and also dense urban fabric with limited drainage capacity and aging infrastructure, as we see, for example, here in Norfolk. And the approach that we use in this study included four different steps, starting from a systematic literature review, finding those NBS types that are most influential uh, in terms of water retention. And as you can see in the picture, for example, we concluded by rain garden, agricultural drainage, ditched green roof, and something like that. And then we used an implementation cost analysis by using some engineering, consulting, information at local level. And then we used invest modeling approach for flood susceptibility mapping. And finally, we use a kind of genetic algorithm, multi-objective genetic algorithms to find the near optimal different solutions. Here you can see three different solutions that we proposed based on cost minimization, maximum water retention, and a balanced approach between both water retention and cost, minimization for the whole city. And the upper maps, shows the land use proposal, and the bottom, maps shows actually the water retention capacity for this land cover land use. And here we compared the results between different solutions, and based on the total relative improvement in water retention, as well as the cost of different nature-based solutions types. And based on this analysis, we found that, for example, a balanced approach with almost 15% total relative improvement in water retention as was supported by previous research in different areas, is the best solution for the land use and land cover, compatibility with different parts of the city, and also the moderate cost, implementation, rather than, for example, the second solution, which was mostly focused on water retention, but with higher, costs, something like installing green roofs, which uh, may contribute a lot to water retention or runoff reduction, but at the same time, they are, costly, and different, practitioners or different governments may, do not prefer to install green roofs in different parts of the city because of its cost is high. And we actually um, proposed different NBS types aligning with this kind of goals. And finally, we found that optimized nature-based solutions significantly improve water retention while lower cost. And this is something different with traditional uniform strategies for implementing nature-based solutions, regardless of the conflicts between water retention and cost and land use compatibility, and without paying attention to trade-offs and how to handle them. And also, we noticed that the genetic algorithms, which are the kind of heuristic methods, are really helpful because they can, propose different solutions, and based on the some, trade-offs and criteria. Uh, Lessons that I learned from, doing these studies, uh, you can see here. The first one is that model choices shapes what vulnerability we are able to see, which is really important. And when we talk about model choice, we talk about the actually model selection, model tuning, model performances, all of the components and characteristics of model actually could impact the relationship between vulnerability, social vulnerability, and disaster outcomes, like flood exposure, like, um, disaster assistance program, and funding allocation and aid allocation between different groups. And second, social vulnerability is really intersectional, not additive. And so it's better idea to actually account for intersectionality in our, modeling approaches. We know that, for example, we have data availability issues, we have data governance issues. These are some of the challenges or barriers that in different countries or different contexts we may face, but here practitioners should, um, consider, actually providing such data sets, at least for researchers, at least for, those who want to, examine the actual native relationships between compounding vulnerabilities. And scale is not neural. It fundamentally alters, inferences, and household level models best align with vulnerability producing processes, as I mentioned. And spatial optimization models for climate adaptation pathways, like, nature-based solutions, outperform uniform, strategies that we can use this kind of different types of algorithms. Some of them are based on multi-objective, some of them are based on multi-criteria. Some of them may use some kind of machine learning algorithms, but still, all of them can outperform uniform NBS strategies, regardless of the context, regardless of the uh, different criteria, conflicting uh, measures. And finally, balancing cost and retention actually yields practical flood mitigation solutions. Uh, I'd like to acknowledge uh, my collaborators from different institutes, from Princeton University, University of Central Florida, California Government Emergency Service Office, USGS, and Guidance Institute of Technology, Texas A&M University, and Politecnico di Milano from Italy. Those who, contributed to these studies. And thank you so much for your attention. I'll stop here and take any questions that or discussions that you might have. Thank you.